In this lecture, we are going to introduce one of the fundamental results of optimal control theory, the celebrated Pontryagin principle of maximum, sometimes also referred to as Pontryagin principle of minimum. And we are going to show how it can be used for finding optimal control for systems with constrained inputs. The lecture is split into a few videos. Here we start by explaining the principle and showing some basic usage. In the next videos, we show some more applications, in particular to time optimal control. First, some recapitulation of the results from calculus of variations. The goal is to find a smooth function y of x that minimizes an integral of some function L of y. The integration is over x from a to b. The values of y at a and b are given. This is the basic version of the problem, but the values of y at the ends could be left unspecified. First order necessary conditions of optimality come in the form of Euler-Lagrange equation, which reads partial derivative of L with respect to y minus derivative with respect to x of partial derivative of L with respect to the derivative of y with respect to x is equal 0. In order to keep the notation short and compact, we often use the subscript notation L sub y minus derivative with respect to x of L sub y prime is equal 0. While deriving fundamental results of the calculus of variations in the previous lecture, we encountered a few interesting functions. First, the partial of L with respect to y prime minus L. But even the partial of L with respect to y prime itself was interesting. We have seen that in physics, when L is given as a difference between the kinetic and potential energies, it can be interpreted as momentum, hence the symbol P. Now we write the former interesting function as P times y prime minus L, and we call this function Hamiltonian, symbol H. Note that while Hamiltonian is a function of y, and possibly also x explicitly, which would make H a function of two parameters, here we formally view y prime and the partial of L with respect to y prime, that we labeled P, as the other two inputs. In total, 4 inputs. This must look very unintuitive, but you will see in a second that this formalism is actually crucial for proceeding further. Now, viewing H as, generally, a function of 4 variables, we find its partial derivative with respect to y prime. It is equal to P minus partial of L with respect to y prime. If you do not feel comfortable differentiating a function with respect to a derivative of another function, you can just relabel the third argument of H as z, just another input argument completely independent of y. We did pretty much the same with the label P, didn't we? And now differentiate H with respect to this third variable z. Once you have it, back substitute for z the derivative of y. Similarly, if we now back substitute for P its original content, partial of L with respect to y prime, we discover that the derivative of H with respect to y prime actually vanishes. This is a remarkable result. You may have already developed some instinct that whenever you see a vanishing derivative, you ask the question if it is the case that the original function is actually minimized or maximized with respect to the relevant variable. How do we proceed in those cases in order to answer the question? We find the second derivative. If we differentiate H sub y prime with respect to y prime, we get minus second partial derivative of L with respect to y prime. Now recall that the second order necessary condition of optimality in the calculus of variations, so-called Legendre condition, is non-negativeness of its second derivative of L, non-negativeness of the second derivative of L with respect to y prime. Combining these two results, we see that the second partial derivative of H with respect to y prime is non-positive. But the implication of this is that whenever Hamiltonian is extremized, it is necessarily maximized. In other words, a necessary condition of optimality of our original problem of calculus of variations is that Hamiltonian is maximized with respect to y prime. Once again, viewing y prime as an independent variable, pretending that we do not know that it's actually tightly related to y, seems strange at first, but it turns out to be the step that enables further progress. If you want to learn more about this issue, have a look at the nice and concise historical survey by Hector Sussman and Jan Willems. But now it's time to switch from calculus of variations to optimal control. Since I wanted to keep the notational conventions for both fields, we now have to relabel the things. While we used x as an independent variable in the calculus of variations, in compliance with most introductory texts, in the control theory we almost exclusively use t, the time, as the independent variable. Similarly, while we did the optimization over functions labeled y in the calculus of variations, in the optimal control setting we almost exclusively consider x, the state variable, and u, the control input, as the optimization variables. Both can be actually vectors. There is yet another change that we must incorporate while doing this transition. Unlike in the basic, unconstrained problem of calculus of variations, in the optimal control problem we do have at least one constraint, the state equation itself. Therefore, we must augment the Lagrangian function with the term that corresponds to the constraints, the product between an auxiliary variable, in optimization called Lagrange multiplier, lambda, and the constraint function. Note that if the order of the system is higher than 1, the product is actually an inner product between two vectors, lambda transposed times f. With this augmented Lagrangian, we can form the corresponding Hamiltonian. After substitution and cancellation of the subtracting terms, we are left with the control theoretic version of Hamiltonian, inner product of lambda and f minus L. Note that in calculus of variations, the Hamiltonian was a function of, among others, the derivative of the function y prime. But here the derivative is directly specified by the function f of x and u, the right-hand side of the state equation. While waving hands a bit, I will claim here that u takes over the role of y prime in the calculus of variations and becomes the third argument of h. Well, this is pretty straightforward for a single integrator system modeled by x dot is equal to u, but not so straightforward for a general f. But I think I'll leave it at it here. Alright, if you forgive me this kind of hand-waving, we have the very interesting fact that on an optimal trajectory given by x star, u star, and lambda star, the Hamiltonian is maximized with respect to the control u at every time t. We label the set of controls u over which we consider this maximization as the capital calligraphic U. Right now it could only stand for a class of functions, but in a minute we will be able to impose some more constraints, in particular constraints on the amplitude. In the meantime, note that the result can also be rephrased in the following way. The optimal U maximizes the Hamiltonian when evaluated along optimal state and co-state trajectories at every time. This is a very interesting and promising result. However, having been derived within calculus of variations, it inherits all the limitations due to various assumptions that we made throughout the development. First, our conclusion about maximization was based upon the assumption that h can be differentiated with respect to u. In some cases, like the LQR problem, this was fine, but there are quite practically relevant situations, such as the use of absolute values in the cost function, when h is not differentiable with respect to u. Sorry. Second, our conclusion about maximization also relied on the fact that the Hamiltonian maximum is achieved by some control u well inside the set of admissible u's. In other words, we did not consider bounds on the control signals, and yet it's actually quite common for real control systems to operate at the boundary of its allowed control signals. In these situations, the vanishing derivative is not a necessary condition for optimization, for the maximization of Hamiltonian. Third, At the beginning of our development of calculus of variations, we characterized the perturbation functions by specifying the vector spaces of these functions. These were sufficiently smooth functions, and we also specified the norms used to measure the size of these perturbations. The zero norm, which essentially gives the maximum of the absolute value, and the one norm, which combines it with the maximum of its first derivative. It turns out, however, that these are not capable to model situations such as the one in which the control signal is a rectangular pulse and the optimization just shifts the pulse in time. All this may sound quite negative, but I'm actually mentioning it only to finally introduce the celebrated Pontryagin principle of maximum. The key message is actually very optimistic, and a simple too. Well, I hope so now after this introduction. The message is, loosely speaking, that our finding that the Hamiltonian is maximized by the optimal control holds good also in situations when those restrictive assumptions, enumerated on the previous slide, are relaxed. Let's now state the Pontryagin principle formally. For a given system and a given criterion, let U star be an optimal control. I'm saying an optimal control because it does not have to be unique. Then there is a variable called costate, we label it lambda, which together with the state x satisfies the Hamilton canonical equations, with the Hamiltonian given as lambda times f minus L. And then the Hamiltonian is maximized with respect to U, with U coming from some set labeled capital calligraphic U. Of course, the corresponding boundary conditions must be satisfied. And that's it. Note that we do not impose any restrictions on smoothness of H with respect to U, and we can also consider bounds on U. In fact, it turns out that the stationarity equation that we introduced and used in the previous lecture, that is, the condition that the partial derivative of H with respect to U vanishes, can be seen as just a special case of this general result by Pontryagin. Maximization of Hamiltonian with respect to U is the crucial fact. Whether the derivative of H with respect to U exists or not, whether the optimal control reaches its saturation value or not. Fine, let me insert now one notational warning. Very often you will encounter in the control theory literature a different definition of Hamiltonian, namely lambda times f plus L. We have discussed this already in some previous lecture, but here I wanted to mention that this choice makes an impact on the statement of Pontryagin principle, because in this case, Hamiltonian is actually minimized by the optimal U. Honestly, it appears that at least in Western, English written books and papers, this definition prevails, and the result is referred to as Pontryagin principle of minimum. The boundary conditions are affected by this too. This we have already seen previously. I just wanted to remind you of this issue because I find it confusing myself, or I used to find it confusing while studying the material. Finally, let's have a look at how we can use Pontryagin principle to solve some optimal control problem. We will consider the standard LQ optimal control problem on a finite time interval with fixed initial and final states. The problem is thus parametrized by the quadruple of matrices A, B, Q, and R, and the initial and final state vectors. Now, the control must be in some set U. This last constraint is something that we were not able to handle within the framework based on standard calculus of variations, that Riccati equation-based stuff. Adhering to the Eastern convention, the Hamiltonian looks like this. And now, applying Pontryagin principle is as easy as writing down the following inequality. Note that the terms that do not contain U can be cancelled right away. They appear identical on both sides. After cancelling these terms, what's left is this. We can also equivalently write it that the optimal U actually maximizes the quadratic function in the square brackets. Simplifying the situation in favor of the core principles, consider a first-order system with a single input. X and U are then scalar variables. The statement of the result is that the optimal control U at every time t maximizes the quadratic function given as -1/2 r times u squared plus b times lambda star times u. The optimization variable u must be within some lower and upper bounds, u min and u max respectively. All this holds at every time. I did not show an explicit dependence on time in the vector version of the problem above to save the formulas from clutter, but you should remember that indeed the condition holds time-wise. Good. Now what? Recalling that r is assumed positive, the function we are trying to maximize has a bump rather than a valley. Therefore, although you are now in this course equipped with general-purpose tools for analysis of constraint optimization problems, namely the KKT conditions, here the analysis is simple. The maximum is achieved either inside the interval or at its lower or upper bound. If inside the interval, the value is obtained following the now familiar procedure consisting in finding the derivative and setting it equal to 0. If this falls under the lower bound on u, the maximizing value is the lower bound. If it falls above the upper bound, then again the maximizing u is that upper bound. This can be written in a compact way upon introducing the saturation function set, parameterized by the lower and upper bound. If we now substitute this expression for u into the state and co-state equations, well, just the state equation in this case, we get a two-point boundary value problem. We cannot have ambitions to get an analytic solution here. Instead, we have to resort to numerical solution. It will be pretty much the same story for free final end case. Recall that without considering the constraints on u, we were able in the previous lecture to find an optimal control in the form of a state feedback. We will not be that successful here. All we can get are just numerical trajectories for the states, co-states, and controls. Finally, note that in general we cannot just take the output of the controller designed by the LQR procedure that ignored the presence of constraints and then simply saturate such control signals and regard this as an optimal solution of the constraint control problem. We really have to solve the canonical equations containing that nasty saturation nonlinear term. Well, I picked this particular example just to illustrate the essential usage of the Pontryagin principle of maximum, but its full power will only be obvious once we consider time-optimal control problems. In order to be able to solve these, we need to prepare the framework for optimal control with a variable final time. The next video will focus on that.